Oh, hi everyone. Could you hear me now?
Yes, we can hear you.
Okay, great. Thank you. Yeah, sorry, 2 minutes late. Let's look at the locality. So last time we talked about locality, and for the locality, we have two kinds. One is the temporal locality, and another one is spatial locality. For the temporal locality, we're talking about visiting the same memory space again and again. This is about temporal locality. And for the spatial locality, bear me a moment. And for the spatial locality, um, that is, we're visiting the neighbor memory spaces around the first visit. That is spatial locality. We talk.
It looks like you muted yourself.
Oh, sorry about that. Let me go back a little bit. For the temporal locality, we're visiting the same memory place again and again. This is called a temporal locality. And for the spatial locality, we're visiting the neighboring spaces around the first visit. That is the spatial locality. And every kind of program that is showing such a memory access pattern, we would say it has either good temporal locality or good spatial locality. And this locality is something we desire. The reason is cache. We talk about the access speed for the memory is 10 nanoseconds. And for the cache, the access speed is 1 nanosecond. We cannot utilize the SRAM to build a memory. That is too expensive. We have to use the DRAM to build like 8 GB memory. The access speed, if we do nothing, the access speed would be 10 nanoseconds for every kind of memory access. And we introduced the cache in the hope of making this memory access faster. And the cache is made from SRAM. Access speed is 1 nanoseconds. And every program who have the good locality could utilize this cache in its full strength and would make the memory access much faster. Here's an example. When you try to access the memory space, the blue dot, if we do nothing, then the access would be 10 nanoseconds. If we have the cache, we would bring the blue dot along with its neighbors into the cache at the same time. And next time, when we want to visit the red dot, we don't have to go to the memory to get the stuff by 10 nanoseconds. We just go to the cache and grab the red dot right away. That takes 1 nanosecond. We make the second memory access 10 times faster because we have this cache stuff. And that's the reason we hope our program could have better locality so that we can utilize the cache more frequently. And we enjoy the 1 nanoseconds instead of the 10 nanoseconds in more frequent way. That's the reason we talk about locality. And also we talked about the two kinds of program last time. One is the two kinds of program, they want to add all the elements in the nested array together. The first kind of program, we add by row, and the second one, we want to add by column. By adding by row, if we look at the memory access, it will have the strike one reference pattern. That is every time we jump one item. That is called a strike one reference pattern. Another one is the adding by column. That is strike n reference pattern. And n is number of columns. That is number of items. Every time we make the memory access, we need to jump across. That is strike n reference pattern. And apparently, the first program, the adding by row, has much better locality. And for the Mara strike n reference pattern, the smaller the number is, the better. So strike 1 reference pattern program is better than strike n reference pattern program. This is about locality. And also we talk about the memory hierarchy. Let me show slides. Memory hierarchy. And memory hierarchy is something like this. At the top of it is our registers. And then the next one is L1, L2, L3. These are 3 levels of cache in our CPU. And the next level is the main memory. And after main memory is the local secondary storage, like disks, SSD. And the last level is the remote storage. And we also talk about how we utilize this memory hierarchy. It's not only a hierarchy shown in this diagram, but also contains the way of using this memory hierarchy. Here's an example. If we utilize the hierarchy, let's see, we have the level K. You can regard level K as a cache, and we also have the level K plus 1, and we can make that as a DRAM. And every time if you wanted something from the contents, let's say we want to look at block 9. And the block 9, the level K has this block 9. So in such a case, we just deliver this block 9 to the upper layer. Otherwise, let's say we want to visit the block number 2, and the level K doesn't have it. And the level K just ask the next level, K plus 1, whether there is a block number 2. In our case, block number 2 is found. So we have to forward this block number 2 into the level K. After it, we can return the block number 2 to the upper layer. So that's exactly the same situation. We give the example of Harry Potter. So when we want to play this movie, from the registers, we ask from the L1 cache. L1 cache doesn't have, so we go to L2 cache to look at, and the L3 cache until we go to the local secondary storage and find the movie. And then we want to play the movie, we have to return the content to the upper layer. So we first go to the main memory, and then main memory go to L3 cache, L2, L1, and then finally go to registers. So this is the way we use the hierarchy of the memory. And also we talk about the cache hit and the cache miss. Cache hit is when you ask block number 9, level K has, that is cache hit. If you ask for number 2, the level K doesn't have it, so that is cache miss. When you have a cache miss, there's 2 possible situations. First one, the cache has empty space. In such a case, you just move the block into the empty space and then done. And how about the other case? Cache K doesn't have the empty space. So in this case, we don't have the empty space, so we need to evict an existing one and replace it with the incoming block number 2. And to evict existing blocks, we have to choose which block we're gonna evict. So we like to keep the popular blocks, and we wanna evict the much less popular one. And there's many different replacing algorithms. We call the cache replacement algorithms to select which block we're gonna evict. And here's a map how we utilize where the cache is. Basically, it's in our CPU. When the CPU wants to look at address, it first checks the cache whether the content is in the cache or not. If it is in the cache, then we would get the content from the cache. Otherwise, we would go to the main memory to find it out. Okay. Okay, so did we talk about the cache organization, these slides, last time? Okay, good. This may be from another, let me see, from another class. Let me hide the comment. And a question from the last lab, I'm planning to post today. It will be the cache lab. It will be very, very relevant to what we're gonna talk about. So expect the cache lab today. Okay, let me go back to the. Okay, here we will talk about the cache organization. We talk about the cache is a smaller size, but have faster access speed. It can help us to make the memory access faster. And what does cache look like internally? Here's the map for the cache. So from this cache, you can see there's many parameters to look at. And the very first one I would talk about is the set number. So in our case, we have the capital S sets from 0, 1, until S minus 1. We have S sets. And for each set, you can see we have multiple lines. We call lines in each set. And we use a capital E to denote the number of lines in one set. If we look at each line, you would find three parts. We will first talk about the block size, which is B. This capital B is the size for this block. This is where our content or data stored in the cache. So cache is something to contain the content as the address. So let's say this is the content, this is the address 100. So the content would go into this block. The size of this block is capital B. So here is where our data is. If we look at the next one, which is the tag. For the tag, we have the number of bits we use for the tag. Lowercase t denotes the number of bits we use for the tag. And we will talk about this tag. It's related to the address. And next one is the valid bit. Valid bit is trying to indicate whether this line is empty or not. If the valid bit is 1, that means this line has data. If the valid bit is 0, that means this line is empty. So you can imagine we have to have this valid bit. As you know, no matter the line is empty or not, we should have some bits over the place. If it is empty, then it could be the random bits. If it is having the content, it will be the content. So if we don't have this valid bit, we have no way to tell whether we should interpret the block as the data or interpret that block as empty. It's just some random bits over there. So we have no way to tell whether the line is empty or not. We have to utilize this valid bit to indicate whether we should treat the block as valid or not. So we have several fields like this. One quite natural question is, we have the address, let's see, we have the address 100 in the memory, in the DRAM, and we know the content is C. When we bring this content and the address into the cache, we should keep two kinds of information. The first kind is the address. 100, we need to keep record of this address. And the other one is the C. When we bring this, so in our cache, we should have some way to record these two kinds of information. We already talked about the C goes to the block. Let's see, first line in the set 0 is a line to receive this content. And we should have some way to denote this 100 in the cache as well. And how we deal with it. From this layout of the cache, we find nothing about address. So how we keep the address of the to indicate address in the cache? We would say that the S bit, the set number, the tag, and also the block offset is a way we keep record of the address. Let me explain how it works out. So let's say this is the address. We have, in our example, the address is 100. And we divide this address into 3 parts. The middle part, the S bits, is trying to decide which set we're gonna select. And the T bits, we utilize the T bits to initialize the tag. And the B bits is trying to find out what is the offset in the block. So for the content C, because it's a content at one address, the size of it should be 1 byte. Let's see, the block size, capital B, is 8 bytes. We need to select 1 byte out of these 8 bytes. So this B bits, the block offset part, is trying to specify the offset within the block. And you can imagine if we, so even though we don't tell the address explicitly, but you can see where this C is related with the address itself. Which set we're gonna use, what is the tag we initialize, and what is the offset within the block. These 3 pieces of information is reflecting what is the address it would be from the memory. So when we bring this address with the content C into the cache, by looking at which set, what is the tag, and what is the offset in this block, we implicitly could decide what is the address of this content, and then find the right space within the block and place C into it. This is how we store information in the cache. So far, do you have any questions? Okay, if you don't have any questions, let me continue the cache part. Some of you may wonder why we organize cache in such a way. It seems like more complicated than more complicated. We have the set, we have multiple lines in one set, and for each line, we have the tag valid, something like that. So why we have such a complicated cache layout? Let me give an analogy from the supermarket case. For the supermarket, we sorry, let me contain my thought. For the supermarket case, we actually have billions of merchandise over the world, but we don't have to buy anything in daily base or weekly base. What we need is a small collection of merchandise. That is where we introduce the supermarket. Supermarket doesn't contain everything around the world. It just contains the popular items that they think we probably use every day. For example, like chips, we want to buy every day or every week. There's a popular brands. We as a customer, they would predict customers would very likely to buy these brands. So they bring these brands to the supermarket and they sell on the shelf, right? So even though around the world there's I would say hundreds of thousands different kinds of chips, but our supermarket just have the collection of the popular ones. So it just works like our cache. So we have billions of data in our memory or in our disk, but the popular ones is quite limited. Our cache is just like supermarket. It just have a small collection of popular data, and that works most likely effective. That means when you want to buy chips, you want to buy some kind of popular merchandise, you don't have to go to the factories where these items are manufactured. You just go to the supermarket around the corner, and then you can grab the content in a very fast way. It's just like cache. Cache has a collection of popular data, and if you want to access this popular data, you can access in 1 nanoseconds. And it's not surprising that the layout of the supermarket is quite similar to the layout of the cache. And for supermarket, we have the categories, right? In each category, this could be the chips, it could be the food section, or it could be the water section, and any kind. We organize merchandises by categories. It's just like the cache, similar idea in the cache. We organize the data by set. Set is just like categories. And then at the same time, within each category, there's multiple shelves in the supermarket, right? In our cache, it looks like the similar one. We have multiple lines, and the multiple lines is like multiple shelves in the supermarket, and then we have multiple lines, and in each line we just have a whole bunch of the a block of the data. It's just the block of the same kind of chips, right? This is just like a block in our cache. So hopefully this analogy could help you make more sense about the layout of the cache, and it's just similar to the layout of the supermarket. And the idea behind the cache and supermarket, is quite similar. We don't need every merchandise. We don't need every data in our computer. There's a set of popular ones we hope to access fast. That's the idea of cache, and also the same idea for the supermarket. And the layout of them is not surprisingly, they're quite similar with each other. This is maybe more fundamental reason is This is usually how we organize resources, by category, by shelf, and by blocks. And maybe this is the reason they share similar kind of layout. Yeah, sorry, my dog was barking now. I read through online and try to solve this issue. It seems like when dog bark more and they like to bark more, they have the androgen. I don't know what kind of they just like it when they bark and fall in love with that kind of barking feeling. Anyway, I'm trying to calm him down. Let's look at the different kinds of the cache. There's 3 kinds of cache based on the different parameters. The first kind is called the direct mapped cache. In this cache, we have 1 line per set. And the second cache is called a set associative cache. In this kind of cache, we have multiple lines per set. And the last kind of cache is fully associative cache. And this cache just have 1 single giant set. And we have multiple lines in this set. So the set number for this cache is 1. Let's look at how we utilize the direct mapped cache. Here's a layout for direct mapped cache. In each set, there's just 1 line. Oh, by the way, this cache part is very important, and this is a core part of this chapter, and for sure they would go into the finals, and also our last lab would be the cache lab. So it's pretty important, and also this is part is also important to understand how cache works and what do you expect if you program and try to write cache-friendly codes. And this part is trying to help you to understand the cache in our computer. So very important. And for this cache, let's look at how we utilize it. So right now, let's assume we have an address to look at. So we have the CPU, and we want to check this address and see what is content at this address. And we talked about the very first place we're going to check out is the cache and see whether this would be cache hit or miss. And let's look at how we decide if this is cache hit. For this address, you can see we divided the bits into 3 parts: the tag part, the set part, and the block offset part. These 3 parts. And by using the S bits, we're trying to decide what is the set number we look at. In our case, it is I, so we look at the set I. We find the set number, we look into the set, and there's just the 1 line in this set. The next step is we try to compare 0110, which is the T bits, with the tag part in this line. And we try to find whether the 2 bits match each other. If there is a match, we further look at this valid bit to confirm whether this line is valid or not. Let's see, it is valid. If these 2 conditions satisfied, the first one is the T bits matches with the tag. The second criteria is the valid bit is 1. If these 2 criteria we satisfy, then we would say this is a cache hit. We find the data in the cache. And in the last step, we look at the block. It seems like there's 8 bytes in this block. We just need 1 out of this 8. We need to find out what is a good offset. We look at the block offset part of the address. It is 100, In this case, we know the offset is 4. So we would select W0 as a result. And we find it's a cache hit, and we find out what is the content at this address. It's W0. And some of you may wonder why we just do it and find the right data. Why W0 is the content at such address? Let me just roll back the timeline to when this data is not in the cache. Let's see, we have the 0110 I and the 100. This address and with the content W0. So let's roll back the timeline. Let's assume right now cache doesn't have this data. So when CPU visits this address, CPU would find no data in the cache, then go to the memory and check out the address, find out it's W0. And the consequence of this cache miss is we would bring this data into the cache. Where are we gonna place this data? We would use the middle part I to decide, we would use the middle part I to decide what is the set index. So we go to here, what is the set index? And then we would find empty space. If there's no empty space, we evict the existing one. We use 0110 to initialize the tag part. And then by looking at the block offset, we find we would go to the offset 4 to place this W0. So if we roll back how the data was placed in this cache, you can imagine when the same address we try to check out, we would go exactly the reverse path to find out what the data is. So we follow so that's the reason we follow this rule, and finally we can find out the W0 from the block. Let me check out the chat window. One question from Isaac. Block offset is just to determine the byte we want to select. That's right. We're trying to look into the block and select which byte for the data. This is a cache hit. And here is an example about utilizing a cache. And at the left side is a cache. This cache have 2 sets. And for each set, we have, because it's a direct map cache, we just have 1 line, and we have 2-bit tag. And the block size is 2 bytes. And this describes what kind of cache we have. The right-hand side is the memory address we're gonna access. We will quickly look at how we utilize the cache to make things faster and how we update the cache as a result. Before we talk about the utilization of the cache, let's roll back and look at the stuff here. When we have the set number, let's see, set number is 8. We automatically decide how many bits we need to denote this set number. In our example, if the set number is 8, we know that the lowercase s, which is the number of bits we use to denote the set index, it will be 3. So 223 equals to 8. That's how we decide the number of bits we use for the set index. So as long as we know the number of sets, we can know the number of bits we use in the address. The similar kind of idea when we decide the block size. Let's say the block size is 16 bytes. And then use the equation over here, we know that for the 16 bytes, the potential offset is 1, 2, 3, 4 until 15. Then what about the number of bits we need to denote this block offset? We need 4 bits. 2 to 4 equals to 16. That's the way we decide we need 4 bits to decide the block index. And some of you may wonder how we decide the T bits. So, for example, we have a 32-bit address. Oh, sorry, the 64-bit address. If we know how many bits for the S index, how many bits for the block offset, and then the remaining would be the tag. So if we have 64 bits, in our case, we have 3 for the set index and 4 for the block offset. It will be 64 minus 3 minus 4, which would be 57. So T bits would be the remaining bits. This is how we decide the T bits. And now let's look at how we utilize this cache. Let's assume at the very beginning we access the address 0000, and the cache right now is empty. Now, could you tell me what is the bits we need for the block offset, and what is the bits we need for the set index, and what is the bits for the tag index? So I will give you 1 minute to do so. We have the address 0000, which is a binary, and we know that we have 2 sets, and we have 2 bit for the tag, and then we have block size 2 bytes. And then my question is, in the address, the bits of the address, how many bits we need for the block offset? How many bits we need for the set index? And how many bits we need for the tag index? Okay. Do you have an issue about deciding the bits to denote set index, block offset? Okay, no worries. Let me go through this one. Okay, let me go through how we make the decision. So the very first question is how many bits we need for the set index. We have two sets. The set index would be 0 and 1. So how many bits we need for the set index? Just 1, right? We just need 1 bits to denote 0 or 1. That is enough. And also for the same reason, the block size is 2 bytes. The offset we need to denote is 0 or 1. So we also need 1 bit to denote the block size. The block offset. If we know these two information, and then we can go to the address from the right side to the left. The first bit is the block offset. This is the first bit. And the next one, the middle bit, the middle part is the set index. For the set index, we only have 1 bit. So right now, we have this 1 bit to denote the set index. And the remaining, the 2 bits, would be the tag. This is how we divide the address to 3 parts. And is that clear? Okay, good. So when we get an address, we need to divide this into 3 parts. And the very first question we need to answer is how many bits we need for the block offset. In our case, we just need 1 bit to denote 0 or 1. The next question is how many bits we need for the block index, the set index. For our case, we have 2 sets. So we need 1 bit to denote the set index. And after we knowing this, from the right to the left of this address, we can find out 1 bit in our case to be the block offset, and then the next 1 bit would be the set index, and then the remaining would be the tag. Let's see, if we know this kind of information, what are we going to do next? First of all, we would bring this block into the cache. And we talked about the block size is 2 bytes. So we not only look at 0000, but also 0001. This is 2 bytes. And we bring these 2 bytes together into the cache. And we select the cache 0 because the set index right now is 0. So we bring to the set 0. And also for the tag, because the tag is 00, so we need to initialize the tag to be 00. By this way, we warm up the cache. Let's assume next step, we want to visit 0001. So in this case, when we have 001, we look at the set is 0. So we go to set 0, and then we find the tag should be a match. And then we have the offset to pick up number 1 as a content. So that will be a cache hit if we visit 1. Any questions? Aaron, we will have another example soon. And that's a cache hit. Let's look at if we go to 0010. If we have 0010, we can look at this will be a cache miss for sure. And we look at the set index would be 1, and the tag still be 0. So we would bring the 2-3 block into the into set 1, and initialize the tag part to be 00, and the 2-3, this 2 bytes block, would be brought to this part. Next time, if we visit 0011, so we look at the set index to be 1, so we go to 1, and the tag is a match, and here should be a value bit. Let's assume that is valid. And then we find a cache hit. We use the last one, offset, to pick up number 3. So this will be a cache hit as well. So far, because we utilize the cache, the 4 memory access, 2 of them is a cache miss. 2 of them is cache hit. So we can compare, if we don't have a cache, visiting 4 memory places, we would need 40 nanoseconds. But right now, because of introduction of cache, we have 20 nanoseconds for the 2 cache miss, and 2 nanoseconds for another 2 cache hit. So the memory access time is decreased to 22 nanoseconds. And next time, let's see, we want to visit 0100. What's going to happen? If we have the 0100, we would find the set index to be 0. Here's the set index 0, and the tag part will be 01. So we go to set 0 and find this 01, the tag doesn't match. So that means we have a cache miss at first. The second part is we need to evict existing blocks for the incoming block. So what would happen is 01 would be gone. We bring 45 into the cache and initialize the tag to be the 01 of 45. So this would be an eviction of existing blocks and replace them with the incoming one. This is an example about how we utilize the cache and how we make the cache to where to hold the data. Okay, so let me use this as an example. Now let's see. We have an address. Start a new slide. Okay, so let's say we have an address of 8 bits. 10101100. Let's say this is the address. We just assume 8 bits for simplicity. If I give you the cache information, and you can decide what is the set index, what should be the block offset, and what should be the tag we look to. let's see, this cache have the block size 8 bytes. And have a sets, 4 sets. If you draw the diagram of this cache, it will look like, let's see, we only have one line. It will be like this. 4 sets from 0, 1, 2, 3. And in each set, we just have one line. And each line, we would have a block size 8 bytes. Now, my question is, if we have such an address, could you tell me what is the set index we're going to look at the cache? And what is the block offset we're gonna look? I will give you 2 minutes. You can tell me the answer. Okay, let's look at together how we decide to divide this address. So at the beginning, we need to decide how many bits we need for each case. So the process is we look at the capital B at first to decide what is the lowercase b. how many bits we need for the block offset. So we have the equation 2 to lowercase b equals to capital B. This is how to decide. For 8 bytes, if you don't want to use a mathematical way, you can think about this way. So for the block offset, it should be any number between 0 and 7. And in order to denote any number between 0 and 7, at least we need 3 bits. So lowercase b should be 3. And about the index, set index, the similar idea. We need we need bits to denote any number between 0 and 3. In such a case, we need 2 bits. After we decide how many bits we need for each category of each field, we can start to denote it. We need 3 bits to denote the block offset. From the right to the left, we will find 3 bits and make that to be the block offset. And after it, we need another 2 bits, which is 0, 1. We need 2 bits to denote the set index. And the remaining, which is 1, 0, 1, to denote the tag. So after it, we can know that the set index we're going to look into is 1. So we would go to the set number 1. And then the block offset is 4. And the tag, if we want to look at the tag, we are trying to match 1, 0, 1. So we would go to the set 1, look at the line, and find what is the tag, and match the tag with 1, 0, 1. If it is a match, and check the valid bit. If it is valid, that will be a cache hit. If we have a cache hit, we would use this offset 4 to pick up the right byte. This is how we utilize the information of cache to decide how we partition the address. So this way we divide the address in this way. So let me give you another practice. We have the same exact address. Let's see, we still have 101, 01100. The address is the same. But I want to give you a different cache layout. And right now, let's see the cache layout. We want to make the block size to be 4 bytes. And for the set index, right now we want to have 8 sets. We still have 1 line per set. And then now let me ask you the same question. What will be the set index we're going to look at? What will be the block offset? In order to answer this question, we need to figure out what should be the lowercase b, the number of bits used for the block offset, and number of bits we use for the set index. So we need to answer these 2 questions. So again, I will give you 2 minutes. You can try to answer what should be the B and S, and what should be the set index and the block offset if we look at the cache. So for the cache, we have 8 sets. So 1, 2, 3, 4, 5, 6, 7. Basically, same address, but now we have a different kinds of cache. The block size right now is set to be 4 bytes. The set index or number of sets we have is 8 sets. We still have 1 line per set. We basically have a different kind of cache. Now the same question. So how we find out the set index, how we find out the block offset by looking at the address right now. Brandon, that's a great comment. Right now, we're direct map cache, so we just compare by once. And then if it match, then we would find a cache hit. Otherwise, we would replace existing one right away. So that's right. We don't have right now do multiple matches. Great. So many of you already know how to do that. Let's go together. When we find the block size is 4 bytes, how we decide the number of bits to denote the block offset? So let's look at the block offset, possible block offset. It will be any number between 0 to 3. So how many bits we need? We need 2 bits. And if we look at the set index is any number between 0 and 7. So if we want to denote it, at the least, we need 3 bits. So by this way, we can find the number of bits for the block offset and the set index. Or if you like, you can use the equation 22s equals to bigger S, 22 lowercase b equals to the capital B. So this is a mathematical way you can decide the number of bits you need for each field. After you decide it, from the right to the left, you find the first 2 bits to be the block offset. And then we need 3 bits, the next 3 bits, to denote as a set index. The remaining 3 bits to be the tag. So after it, we know the set index we're gonna look at is 0, 1, 1, which is 3. The block offset is 0. The tag we need to look at is 1, 0, 1. So the consequence is we go to set index 3 and look at the line it has. Try to find a match whether the tag part is 101. So we can decide whether it will be a cache hit or cache miss. if this is a cache hit, we use offset 0 to pick up the byte out of these 4 bytes. So from this example, you can see for the same address, we use the same address for different 2 caches. And the parameters of the cache decides how many bits we need for the block offset, how many bits for the set index. And finally, the parameters of the cache decides how we partition the address into 3 parts. And after it, we can know which set we should look at. And what is the offset of the block, we need to pick up the byte. And what will be the tag, we're gonna try to find a match. This is how we utilize the direct map cache. Any questions so far? Okay, great. Let's continue. And we can have other kinds of cache. So this is called a set associative cache. The only difference is we have 2 lines or more in one set. And when we try to compare this, try to find a cache hit, we would use the middle part as bits as usual to find what is the set index we want to look at. And then we use the T bits to match with the tag and try to find out whether there's a match. Here is the third kind of cache we call the fully associative cache. In this case, the fully associative cache, we just have one set. In this one set, we have multiple lines. And if we look at the address, you will find we have no set index. The reason we don't have set index is because we only have one set. We don't have to include any bit to select which set, right? We only have one choice. So we don't need anything about the set index. The address would be having 2 parts, the tag part and the offset part. And if we look at how to make a match, we find the tag part 0110 and compare this with each line. So the very first line have the tag 1001. It's not a match, so we pass. The second one is 0110. Seems like it's a good match. But if you look at the valid bit, it is 0. So it means that this line is empty. So it will be a cache. So this line we have to pass as well. So the third part, we have 0110 as a tag. That's good. And if we look at the valid bit, it's 1. So we find a match. This means it should be a cache hit. And then we use a block offset, which is 1004. We pick up W0 as a result. This is how we find a match in a fully associative cache. And the only difference that compared with the previous direct map cache is in each set, there will be multiple lines. We have to compare each line and until we find a cache hit. This is called fully associative cache. And right now we have 2 minutes left. So we would stop here, do a summary. Next class, we will talk about what is the pros and the cons of these 3 kinds of cache. And today we talk about the cache layout. The cache layout have 3 important parameters: the set index, the block set, the block offset, and also the tag bits. These are three parts. And we talk about when we have an address, we divide the address into three parts and then use the middle part as bits to select which set we're going to look at, and the right bits, right block offset to decide what is the block offset, and the tag part trying to find a match or not. We make the analogy that a cache is quite similar with the supermarket. They are all the collections of popular items or data. And when you access the popular items of data in the supermarket or the cache, the access speed is quite fast. And the layout of the cache is quite similar with the supermarket. We have the categories. In the cache, it is a set. In the supermarket, we have shelves, and in the cache, we have lines. And the layout of them is quite similar. So the organizing a supermarket is quite similar as organizing a cache. And based on the parameters, we have three kinds of cache. Direct map cache, which is just one line per set, and a set associative cache, we would have more than one lines per set. Last one is fully associative cache, which just have one set and multiple lines. And also we talk about example how we initialize it. When we try to decide which set we should go to, we first figure out what is SBT, and then we can divide the address into three parts and find out the set as a result. We show the example how we initialize the cache, or prime the cache, and then utilize the cache when we try to have a good locality. And sometimes we need to evict existing one to accommodate the incoming one. And we give several exercises to look at how to decide the parameters and try to partition the address into three parts. Okay, that will be our today's content. Yeah, if you have any questions, I will be around. Thanks for attending, and happy holidays.